your decision to accept.
Right. Sure, I'll do that.
Oh, I'm hearing audio. I'm hearing us. Cool. I see that I'm on the camera. Sorry for the technical difficulties this time. So hi everyone, and welcome to another night of Astronomy on Tap in Kingston. It's now 2021. I know it's been a while since we've been here with you. And as it's 2021, I thought it was going to mean that all the world's problems were solved. But alas, I don't think that's so. I think we're still dealing with some stuff, but at least we have each other during today. So a big thank you to all of you tuning in to join us to leave the world behind and hear from some truly stellar scientists. I'm Mark Richardson, I'm your host tonight, the Education and Outreach Officer at the Arthur B. McDonald Canadian Astroparticle Physics Research Institute. So we're a collection of scientists, universities, and research labs across Canada trying to uncover some of the biggest mysteries of the universe by looking at some of its smallest things. So I'm here in Kingston, Ontario. I'm an astrophysicist by training. As I've already revealed in the chat, that is me. I got my PhD in Arizona at Arizona State. So yay for those joining us from there. I wish I could go back to Rum Bar and get a nice drink. And so my research has been studying how galaxies form and change over time. So one of the speakers tonight has a very special place in my heart. I'm really looking forward to hearing what she has to say. So I'm truly excited to hear from the different visitors that join us today. I'm excited for all the talks, not just that one person. So I love taking these kinds of opportunities to share astronomy with you. I see these events as opportunities to share with everyone at home how amazing, exciting, and useful science is, and how it helps us overcome some big problems, be it a pandemic, or climate change, or the flavor of the week. So I'm really happy that we're all able to come together, even now, to events like this, and that you're able to join in live. So hello to everyone joining from home, whatever lands you call home. For me, home is the lands of the Cataraqui, now Kingston. It's the traditional lands of the Anishinaabe and the Haudenosaunee people, and many Indigenous peoples before them. And I'm truly appreciative that we were all able to learn tonight from our respective homes. Now, as a settler personally from Halifax, Nova Scotia, the traditional land of the Skin Dressers district of the Mi'kmaq, and once the home of the racialized community of Africville, I recognize that my ancestors were complicit when these people had their access to those lands removed. And as an astronomer, someone who really revels in the wonder of both the land below us, but the universe above us, and the planets and the skies, I recognize that this science relies on facilities that use traditional and sacred lands of various Indigenous peoples who have a voice to add to this science and who should be gatekeepers to those spaces. So I reflect on these aspects of my identity and how they afforded me certain privileges in my academic life. And so to all of you, I urge you to think of the connection that you have with your land, with the land around you, and the gift that we all have to learn wherever we are. I also encourage you after tonight's event to explore the website whos.land and learn about the past people who have lived where you live. So moving forward, let's reflect and work together towards decolonizing our spaces to make them ones of friendship, love, and access for all those in our community and beyond. So the plan for tonight is simple. It's meant to be a conversation more than a lecture. So grab a drink, open your minds and imaginations, and say hello from the comments section. Let us know where you're joining us from. We're going to hear tonight from 3 astronomers and physicists. I can't pick up a drink without at least taking a drink. So we're going to hear from 3 astronomers and physicists who all do very exciting but quite different research. We're also going to have a special, actually we're not going to have the special format. We really wanted to have some people come on for trivia, but we will be doing kind of our standard trivia. There's a form linked in the description. If you happen to join us on Facebook, you saw we posted a picture of some of the prizes that you can compete for this week or this month, and some of them will be like a McDonald Institute mug. There's t-shirts up for grabs, and there's some other items as well. And it's not just the highest score that wins some. We'll do a random draw from everybody that submits answers, and you'll win something too. So before we get the ball going, and I guess at this point I should share my screen. So let me just get things going. You should be able to see that. So, as I said, we have 3 great speakers coming out today. And before we get going, I did want to just mention a little bit about our sponsors. These are the sponsors that really help us, particularly when we do get to meet in person. I do appreciate that on these times when we're online, we get so many more people able to join in. But when we do happen to congregate at our local pub, the Kingston Brew Pub, right here, it's a lot of fun. And the reason those events get to happen is because we have sponsors like Queen's University, the Queen's Observatory, the McDonald Institute, who's also hosting the channel that we get to run on right now, as well as these communities locations that donate prizes for when we all meet in person. But before I welcome on our first of our speakers, I do recognize that it's been 4 months since we've been together. And we always like to start off with a little bit of space news, or like I'm going to call it a bit different today, news from space. And more news than just the fact that all of the Muppets will be close to you at home at Disney Plus soon. They did not pay me to make that announcement, but I love pigs in space. So the first thing I want to announce is that in November, scientists at the Borexino experiment in Italy, they published that they had observed neutrinos from the sun from the CNO fusion process at its core. So here's a really cool picture is an artist rendering of what the Borexino experiment looks like. It's quite huge. You see people inside dealing with all those little photosensitive detectors. And so they said that they detected neutrinos from this CNO reaction. It's super exciting because until now, we've only seen neutrinos from the sun that are emitted from something called the PP chain. And if you know anything about how the sun burns its fuel, you're probably familiar with the PP chain. And that is this little artistic picture. In essence, it's bringing 4 protons together to make a helium atom. And it turns out that the PP chain is really common in low-mass stars, like our sun, and makes up over 90% of the energy that it produces. But in higher-mass stars, we don't think that reaction alone can explain the temperatures and the energy production that they have. And so instead, there had to be this other process, and that process, we think, is something called the CNO cycle, which uses carbon, nitrogen, and oxygen as a catalyst to actually slowly bring these protons together. And it's very temperature sensitive. And so it's important for big stars, we think, but it only happens like really, really rarely in the sun. So long though thought to exist, we just hadn't had proof that it actually exists. It's nice to have a theory that this thing is happening, but really observational evidence is always key. And so this observation from Borexino is providing that. And so now that we understand that this thing is actually a reaction that happens in stars, it's painting a better picture of how bigger stars live their lives and eventually die. The next month was December, and so we had a really cool thing happen. So last December, we were very lucky to see that there was a cosmic get-together that defied all social distancing rules. Jupiter and Saturn got so close together in the sky that you could actually barely tell them apart unless you were really, really young and a good whippersnapper. And so if you had a telescope or binoculars, you probably could see them. And here's a beautiful shot in, I believe, a telescope where even though these things are so small, when you zoom them in with a telescope and you see them in all their beauty here, you can see the moons of Jupiter here at the bottom, see the rings of Saturn. In the same shot, you get to see the two planets. So this was really, really cool. It happened on the winter solstice as well, so pretty rare. The last time this kind of conjunction happened was 400 years ago. The next time it's going to happen is in 2080. I hope you got to see it, but if not, there's lots of really cool images on the internet to let you see it. Not quite the same as seeing it live, but And last but not least is an update. So in our August Astronomy on Tap, I told you about the Perseverance rover. So on July 30th, NASA launched this rover to go to Mars. Perseverance, it's known more familiarly by its scientists as Percy. Way less syllables when you're talking about it a lot. The launch was flawless, and now it's less than a month away from arriving at the red planet. In Mars, we can assure you can see Mars behind me. I'm wearing its colors today. Mars, we can assure you that Percy got a good wipe down with sanitizer first before it arrives. So Perseverance is almost there. It's almost identical in size to the Curiosity rover that landed in 2012. It's about the same size as a Tesla sedan. And if you recall, though, when it gets to Mars, it has 7 minutes of terrifying feats to do to get from screaming speed from interplanetary travel to the surface of Mars without leaving a crater. And that involves parachutes, a sky jetpack that you're seeing here, a sky crane, and more. And so this is going to be happening on February 18th. We'll have an exciting 11-minute delay as we wait to hear how it went. But what we're going to be doing, we recommend that you tune in, is on February 18th around 2:30, 3 o'clock, we'll be starting a panel. And there's a Facebook link, which I'll post in the comments as soon as I'm out of here. And we hope you can join in. We're going to have some really great experts as well, some of them from Arizona, who'll be talking a little bit about both how do you do this interplanetary travel and what are the cool sciences that we're going to do once we're there. So tune in on February 18th and register now so you see any updates. Alrighty, so that's it for science or space news today. We're going to introduce our first speaker now, and then we'll have some periods of trivia, and hope that you get to stay with us the whole night. So our first speaker is Simran, and Simran, I encourage you to unmute yourself and show your camera. Simran, you're a master's student at Queen's University and a researcher with the McDonald Institute studying theoretical cosmology. She studies gravitational waves produced during the expansion of the early universe. And before coming to Queen's, Simran did her undergraduate degree at the University of Toronto in physics and astronomy. While she was there, she was part of the LightBird collaboration and worked with the Canadian Space Agency, to figure out how well the LightBird satellite will be able to determine what occurred during those earliest moments of the universe right after the Big Bang. Alongside her research, Simran spends a lot of time doing a variety of science outreach for events ranging from organizing virtual classroom visits for Let's Talk Science program to running a virtual national symposium on astrophysics for high school students. Of course, when she's not busy doing all of that, Simran loves to do a lot of baking, everything from loaves of sourdough to cakes, and maybe you get to do a lot of that right now with us all staying inside. And I'm going to post a link in case anybody has some high school kids, they want to join in for the Let's Talk Astrophysics Symposium, we can have them join for that. So Simran, I'm really looking forward to hearing what you have to say about your really cool science today. I'm going to turn off my camera and encourage you to share your screen.
Great, okay, I'll do that. Share my screen. Are you seeing it? Okay, great, okay. So today I'm going to be talking about ripples in space-time, studying the early universe. So I'm going to start with the takeaway. And don't worry if it sounds really daunting or you don't really understand what it means. I'm hoping by the end of the talk you'll be able to understand the statement. and that is that gravitational waves can be used to understand the earliest moments of the universe. And this is really important, because if we can understand how the universe began, we can understand why it evolved the way that it did. So I'll start with what most cosmologists do when they give a talk, and I'll give a brief history of the universe. So you can see here on this side here, it started with the Big Bang. Then there was this period of really, really fast expansion, which was called inflation, and it'll be one of the main points of the talk. And that happened within like a fraction of a second after the Big Bang. Then you had things like protons, neutrons, electrons, the normal matter that makes up like you and me, or like a table, gets formed, and that all happens in the first 3 minutes. Then, when the universe was 300,000 years old, you have this time period known as the cosmic microwave background, which I will explain shortly. And then nothing really happened until the universe was about 2 million years old, and that's when the first stars and galaxies started to form. And then if you fast forward to today, when the universe is about 13.8 billion years old. So I'll explain a little bit about this cosmic microwave background. But before I can do that, picture the Earth. We know the Earth is a sphere, and it's in 3 dimensions. But it would be really annoying if every time we wanted to figure out something about the Earth, we had to look at a globe. So what we do is we project it down to 2 dimensions, or a map. And that's what you're seeing here. This is a map of the Earth. Well, when we're taking data of the universe, we're taking it going outwards from the Earth in all directions, and we get a sphere of this data. And just like the Earth, we can make a map of this sphere of data. And when we collect the data of when the universe was 300,000 years old, we get something known as the cosmic microwave background. So this is a map of data from the COBE mission of this CMB. And as you can tell, it's all the exact same temperature. It's all negative 270.4 degrees Celsius. It's actually so much the same temperature. When you take away this average temperature, you're left with really, really small temperature changes on the order of microcelsius, or 0.000001 degrees Celsius. Well, this is really weird. We don't expect everything to be essentially the same temperature, and I'm going to try to explain why. Imagine you were having a dinner party, and you invited 2 people over, and both of those people brought potato salad. Well, this is kind of weird, but you can dismiss it as a coincidence. Even though they had hundreds of dishes to choose from, you can kind of explain why 2 people would bring the same dish. But now imagine you invited 1,000 people over, and every single one of them brought potato salad. Not only did they all bring potato salad, they all brought the exact same amount. So they all brought 1.000001 kilograms of potato salad. Well, this can't really be dismissed as a coincidence anymore. All these people must have talked to each other before the party or been in contact to all have brought the same amount of potato salad to play this hilarious prank. Well, this is similar to the photons or the light particles in the early universe. They must have all talked to each other or been in contact to be able to be the same temperature at the cosmic microwave background. But if you remember, I said that CMB was when the universe was 300,000 years old. Well, if you think about that, that means that the volume that these light particles could have traveled in that amount of time would be only about 1 million light years across. But that only corresponds to a degree on the sky. So anything larger than degree patches on the sky shouldn't be the same temperature. But it is. And that's one of the biggest motivations for inflation. If you recall this history of the universe, you can see here that during inflation, the universe expanded extremely fast. It's continuing to expand going forward, but at a much more modest rate. And nothing really compares to how fast it expanded during inflation. But one thing I haven't told you is that we can't actually see before the cosmic microwave background. And I'm going to try to explain why. Imagine you were at a party, and it was really busy, and you wanted to get to the other side of the room. Well, you're going to hit into a lot of people and bounce off of them, and it's going to take you a really long time to get to the other side of the room, and you might not even be able to get there. But as the night goes on, people get tired, they go home, the party might look something more like this, where it's going to be really easy to get to the other side of the room. You're probably not going to hit a single person. Well, this is kind of like the photons or light particles in the early universe. There were so many protons and electrons and neutrons around, that these light particles kept hitting into all of them and weren't able to free stream towards us until a certain point where they started combining. So these protons and neutrons and electrons combined into atoms, and there was now enough room for the light particles or photons to free stream towards us. And this point of time we can measure, and that's the cosmic microwave background. But if inflation happened before the cosmic microwave background, how can we detect anything about it if we can't see before it? Well, scientists thought of a pretty cool way, and that's using gravitational waves. Recall in 2015 when LIGO, or the Laser Interferometer Gravitational Wave Observatory, detected 2 black holes merging. You can see an artist's rendition of kind of what this would look like on the screen here, where you have 2 masses orbiting each other, and they're causing these ripples to go out in that fabric of space. These ripples are known as gravitational waves. And this detection was so important that they actually won the 2017 Nobel Prize in Physics for it. But we know space isn't just a fabric. There's more dimensions. So consider this on like a 3D grid of space. And you have one of these masses moving around. Well, you can see as it's moving, it's causing that lattice, that grid of space, to be bent in different ways as it moves around. But we actually live in 4D space-time. So we have these 3 dimensions of space, but we also have time. So here, there's just the one mass in the center, and then you have this grid of space. And at each point on this grid, there's these little clocks that are showing you how fast time moves. And you can tell that time moves very different when you're far away from the mass than if you're really close to the mass. During inflation, you can kind of have these types of things happen where the space and time are being distorted, and that causes gravitational waves to be emitted. And unlike the photons or light particles, gravitational waves don't care how many people are in the room. They're kind of like the music in the party. No matter how busy or empty the party is, that music or the gravitational waves can get through it. So then we can try to detect them. We do that using things such as LIGO, which I mentioned earlier, or the Laser Interferometer Gravitational Wave Observatory. And here you can see photos of them. There's 2 locations, in Washington State and also in Louisiana. And then you could also use things that are future experiments, such as LISA, which is the Laser Interferometer Space Antenna, which is 3 satellites set up like a triangle that's going to orbit the sun like Earth, which you can kind of see here in this GIF. Well, there's the sun in the center, then there's the Earth, which is orbiting the sun, and you can see this triangle, that's LISA, and it's orbiting the sun like the Earth. Well, I'll try to explain how these types of experiments can look for these gravitational waves. So here's an example of the LIGO setup, so that L. So the way that LIGO works is it has this laser or this light that gets emitted. And then it'll hit this mirror and it'll split the light waves apart. And they'll go all the way to the end of the arms, they'll bounce off, and they'll come back. And when they get to that point where they got split up, they'll recombine. But they'll combine in such a way that they cancel each other out, and there's no light signal there. But as a gravitational wave goes through this detector, it causes the arms to stretch and shrink, which causes this to have a flashing light. So it's not canceling out the whole time anymore. You're getting this flashing signal. And this flashing signal is what scientists measure, and that is detecting the gravitational waves. But you might be thinking, well, what if there's an earthquake and it causes the arms to move around and get this flashing light? Well, that's why they have 2 different detectors in Washington State and Louisiana. Because if there's an earthquake, only one of them is going to see that signal. So if they have 2, they'll only know if it's a gravitational wave if both of them are seeing that signal. Well, once we can try to detect the gravitational waves, we can put them on a plot like this, which looks really scary, so I'm going to go through it piece by piece. So theorists like myself can think of models of inflation and try to figure out how much gravitational waves do we think would be produced. And then we can put them on a plot like this. On your y-axis, you have the strength of the gravitational waves, where the higher you are, the stronger they are, and the lower you are, the weaker they are. And then you can put that against the energy. So here is a bunch of the amounts of gravitational waves we expect from different models of inflation. Then you can look at the experiments and figure out how much gravitational waves could they detect and put that on this plot. So this gray region here is what these experiments like LIGO and LISA could detect. You can also use cosmological observations, like measuring the cosmic microwave background, galaxies, element abundances, and figure out how much gravitational waves could they detect, and put that here. Well, one thing to notice is that these models of inflation aren't overlapping any of these shaded regions. And for these experiments to be able to detect these gravitational waves, they need to be overlapping. So this motivates trying to increase the sensitivity in this regime. For example, if you get better experiments for measuring the CMB in galaxies, you can lower this bar here. And another option is building a gravitational wave observatory, kind of like LIGO or LISA, but to be able to measure these higher frequencies, these higher energies. So now we're just going to go back to the takeaway. We know that gravitational waves could be produced by inflation, and we can figure out how much we expect. Then use experiments such as LIGO and LISA to see if they're able to detect these gravitational waves. And if one day we are able to detect them, it'll help us understand how our universe began and why it evolved the way that it did. Thank you. I can take any questions now.
Hey, thank you so much, Simran. Really, really, really cool talk. And there was lots of discussion happening in the comments, not just by your Aunt Holly, but also from other people. So the first question, which was asked by Sean, was, do gravitational waves travel the entire universe? Do they go until they reach the end of the universe? Do they dissipate? Like, what happens as they travel through space? Do they
okay. Yeah, so the farther gravitational waves travel, the less strong they will be. So since the universe is pretty infinite, there's going to be a point where you wouldn't really be able to detect that signal at all. By the time these gravitational waves get to Earth, like LIGO, for example, the changes that it measures is 1/10,000th the radius of a proton. And protons are really, really small because they're only part of an atom, which is really small. So even by the time they get to us, even from huge black holes merging, it's really, really small changes that they're looking for.
And am I right in reading these models then that, like, the models from inflation are even smaller than what, like, the strength is even lower than what I guess LIGO is looking at?
Yeah. So yeah, for some of them, yeah, these are even lower, but these are particularly lower energy models. So with lower strength of gravitational wave models. There are lots of models of inflation. Since we haven't been able to measure it yet, we don't exactly know how it all happened.
Yeah. So another question from Sean, but it has a follow-up question from somebody else, is, with the newer measurements of the seed of the expanding universe, and as those measurements change, and maybe there's, like, we're still updating those with new experiments, why do we think it's changing, and what could that mean? So I guess it's more going back to, like, the general question of cosmology is, like, why are we getting new answers for the expansion of the universe? Like the expansion, like, I guess it's the Hubble constant.
Okay. So yeah, I guess, yeah, if it has to do with the Hubble constant, so basically what that parameter that they mentioned measures is how fast the universe is expanding. And you can try to measure that using things like the cosmic microwave background or really early universe stuff and figure out how fast we would expect it to be expanding today, given all the things we know that makes up the universe. But we can also try to measure it with things that are a lot closer to us and exist at like a much more recent time, like other galaxies and stuff around us. And currently, those two measurements aren't agreeing. So either something is either new measurements will help us figure out if one's wrong or if there's just little things that need to be fixed, or there's something else happening that we don't actually know about yet. But as we get better and better experiments, we'll be able to figure out, which one of those it is, and yeah, if there's new science to be figured out.
I see. So it's like, it's not necessarily that it's changing, it's just our ability to measure it is changing depending on how we do the measurement.
Yes. Yeah.
Oh, wow. So, and then the follow-up question was actually to the first one. I failed as host. And it's, what happens to gravitational waves when they hit things? Like when they hit the planet, do they sometimes reflect? Do they go through it? Do they get absorbed?
Yeah, so when they hit things like, for example, when they hit the planet, they actually cause the planet to stretch and squeeze. And the way gravitational wave works is like if you have like a circle or a sphere and a gravitational wave was going to hit it, it would squeeze one direction and stretch out the other one. So it would look kind of like this, but this is extremely exaggerated. But that's kind of what it does for them. It stretches and squeezes it, and that's how we're able to measure it.
Oh, wow.
Yeah.
And the question I have for you is, if and when these are measured, what does that tell us about this inflation period?
Yeah, so that will let us know exactly when inflation happened and at what energy inflation happened. Because right now we have like a pretty good picture of what happened in the universe at about 3 minutes. But before then, we're still trying to figure out those questions. So it'll help us actually be able to nail that down and know what energy inflation happened at and exactly when it actually occurred.
Thank you so much. I think we are going to move on to our first round of trivia. I want everybody from home, let's thank Simran again. Feel free to keep asking questions if you think about them later. I think we'll have an opportunity at the very end to get all the speakers back and just see if there's any last questions that are hanging out there. But yeah, so I'm going to begin the first trivia round, and I want to remind everybody in the description under the YouTube video, if you stop being full screen, then there should be a link. You can put your answers in there for the first round. We're going to split it up into two between the next two speakers. And here we go. So question number one, how much would a 150-pound person weigh at the center of the Earth? And if, so my accomplice, who usually is helping me, and today he is helping me from the background, it's Nick Aurora. He has not seen the wonderful, scientifically inaccurate movie, The Core. But if you were in the core, if you were Hilary Swank and you got to go all the way to the center of the Earth, and you were a 150-pound person on the surface, how much would you weigh at the center of the Earth? Alrighty, question number two. What constant is referred to as the universal clock? What sets the universe's clock? I will come back and repeat all of these questions one more time. Question number three. Which one of the following planets radiates more heat than it gets from the sun? Is it Jupiter? Is it Saturn? Is it Neptune? Or is it all of the above? Which of the planets are releasing more heat than it's receiving from the sun? Jupiter, Saturn, Neptune, or all of the above? All right, question number four. Name that scientist. Who is this woman? Name that scientist. All right, and again, I will be repeating these one more time. Question number five. David Bowie played which famous inventor in a Christopher Nolan film? David Bowie played which famous inventor in a Christopher Nolan film? And that's all the questions for round one. So we will do a repeat. Question number one, how much would a 150-pound person weigh at the center of the Earth? Question number two, what constant is referred to as the universe's clock? Which constant could it be? Question number three. Which of the following planets radiates more heat than it gets from the sun? Jupiter, Saturn, Neptune, or the famous planet, all of these? Question 4 is name this scientist. And last but not least for this round, question 5. David Bowie played which famous inventor in a Christopher Nolan film? All right. Does anybody need any repeated? And of course, when I'm doing this, I can't see your comments anymore. So let's see if there's, I can also write them in the comments if there is a request for any of these to be repeated. So at this point, that ends the first round of trivia, and I want to invite our next scientist on to the show. So Alyson, if you would like to share your camera and unmute yourself. Hi, Alyson. So our next speaker is Dr. Alyson Brooks. Alyson is an associate professor of theoretical astrophysics at Rutgers, the State University of New Jersey. She uses state-of-the-art simulations of galaxy formation to understand galaxy evolution and interpret observations. Alyson is particularly interested in understanding her own Milky Way and its small neighbor galaxies. So originally from Minnesota, one thing that most people don't know about her is that she used to luge when she was a kid. And so when did you stop?
I stopped at about 5th grade, actually.
Wow.
So, yeah,
that sounds like a very...
They had an ice track, and they switched to a snow track. So there's actually 2 types of luge. And when they got to the ice track, I said, I'm done. I'm out of here. So.
I see. Well, thank you for sharing that with us. I'm really looking forward to hear about how you simulate galaxies and the cool science you can do with that. So I encourage you to share your screen, and I'll get out of here.
Okay. All right, then. I think that should be where we're at. So yeah, thanks for having me tonight. It's really fun to be here. I'm looking forward to sharing with you all some of the work that I do on galaxy simulations, and I've been particularly excited for the last few months because I just finished running after several years, the highest ever what's the best way to say this? Highest ever resolution simulation of a Milky Way mass galaxy that's ever been published before. And so you're actually looking at it right now. What you see in the center of this image in red, or the orangish coloring there, is actually dark matter, right? So that's one of the essential ingredients in making galaxies. So I'm going to tell you all about that today. But something like our own Milky Way would be sitting right down here at the very center. Just like this is the actual simulated Milky Way galaxy that we made. And it is surrounded, extending out, 10 times further than the galaxy than you actually see, by dark matter that is gravitationally bound to it. And you can see all these little bright knots in there, right? All these little dense, bright knots are actually small galaxies that sit inside the Milky Way. And so the other thing I'm particularly interested in is understanding these other galaxies that are our neighbors. Okay, and so this image highlights a few. There's some big and bright neighboring galaxies in this simulation, but then some of them start to get very small, very faint, and I'm not even sure if you can see that in this box down here, there is a dwarf, what we call a dwarf galaxy. It is very faint and it is very puffy. And so it is actually very hard to see, but it is a galaxy. And I'm very interested in understanding where things like this come from. Okay, so here's our Milky Way, right? So you're probably used to seeing beautiful images of spiral galaxies that look something like this. This is one of my favorite images. It was made by Robert Hurt, who's at the Spitzer Science Center. And it's based on real data. That's why I really like this. So, the Milky Way, in the Milky Way, the sun is sort of sitting out here, sort of halfway out from the center of the galaxy towards its edge. And at the time that Robert made this image, we could really only see, say, this half of the Milky Way that we're sitting on, right? This near half here. And that's because there's a lot of gas and there's a lot of dust between us and the stars on the other side of the galaxy. And so the light from those stars doesn't necessarily make it through that gas and dust in the visible light, and it takes us building very far infrared detectors to be able to see through all that gas and dust to the other side of the galaxy. So what Robert did when he made this image is he just assumed that whatever we see on this side, he was mirror it, put it on the other side of this image. And so it's a nice symmetric galaxy. And what we're finding as we're able to now start seeing towards the other side of the galaxy is that it actually does look a lot like this image. And so I think that's just kind of neat that it worked out that way. Okay, but what you see in an image like this is, of course, these beautiful lanes, spiral arms here, the dark spots. That's dust, which sits in the gas. So dust is really just small molecules sitting in the gas of the galaxy. And the bright little red spots are the places where lots of stars are forming. So it's the gas and it's the stars. But of course, what you don't see is that the Milky Way is also surrounded by dark matter. And in fact, there's a lot more dark matter than there is ordinary matter, right? So this is a pie chart of the energy in the universe, right? The energy density in the universe. And so most of the universe is in fact made up of this stuff called dark energy. No idea what it is. We'll just call it dark energy because it is causing the fabric of space-time to expand. Okay, and so when I run my simulations, this is actually in there causing stuff to move apart from each other. But what I also have to put in the simulations are these two things, right? This is the matter in the universe. This is the stuff that actually has mass. And you can see that most of the mass in the universe is actually made up of this stuff called dark matter. We don't know what it is, but we know that it has a lot, it exerts most of the gravity in the universe. We see evidence everywhere for its gravitational influence. And so, you know, the stuff that makes up you and me, the ordinary matter, is really just a small percentage here, 5%. And so if I'm going to make a galaxy, I got to include all of this stuff in there in order to get a real galaxy, something that looks like a real galaxy out. Okay. So this is a movie of one of our older simulations that my collaborator Andrew Ponson made. And this is just dark matter. There's no gas and stars in this particular movie. We're starting from the Big Bang, essentially. So you can see that was the universe expanding. And what I want you to notice as we go on is that as the universe expands, this interesting web-like structure starts to form. We call this structure formation in the universe. It's gravity basically pulling on the areas of the universe that are just a little bit more dense. And so it collapses under gravity into these sheets and then these filaments. And then matter flows along these filaments, creating these bright knots in the universe. So for instance, you see this bright knot of dark matter collecting. And we call that a dark matter halo. And we think that galaxies live at the center of dark matter halos. So this movie picks up at the same point where the last one stopped, but now you're looking just at the gas and stars in the simulation. And in fact, we'll do a nice fly through of that particular galaxy. And we'll come up on this set of galaxies here, which are all about to actually merge together. And the reason I like this movie is then it steps back and we get to see where all the dark matter is, right? So there's all of this dark matter surrounding this galaxy. And in our own Milky Way, you know, our own Milky Way is rotating at about 200 kilometers per second. And if there was not dark matter, there's not enough gas and stars in our own galaxy to actually keep it together when it's rotating that fast. We have to have the gravitational influence of dark matter holding all that stuff together. Otherwise, the galaxy would go flying apart. Okay. All right, so here is my new simulation, my very high resolution simulation of a Milky Way mass galaxy forming. And this is a view you probably don't usually see. So you're used to seeing, you know, the beautiful spiral galaxy sitting, forming in these simulations. And the Milky Way in this particular movie is sitting right down here in this white bit. Okay, it's actually saturated out, so you can't see the spiral galaxy forming. What you're actually looking at instead is what we call the buildup of the stellar halo. So what you also usually don't see in these images of pretty spiral galaxies is that there is all these stars out beyond the spiral, but they don't contribute much light. They contribute only about 1 or 2% of the light in the galaxy. And so they don't show up in these images, but it's just full of structure, right? You can see what's going on is there's these small galaxies that are falling in to the gravitational influence of the Milky Way, and some of them are being completely torn apart. You can see they make these beautiful streams and these big shells. And I should mention that okay, so when I ran the simulation, there's dark matter, gas, and stars, but I'm only showing you the stars right now. So I'm not showing you the dark matter. I'm not showing you the gas. And the stars here are color-coded by essentially their chemical contents. So the amount of heavy elements, the stuff that gets created in stars. And so if it's a really dark blue, then it has not very much heavy elements. If it's a little bit lighter blue, then it's got a little more heavy elements, and then so on up to red. And then the Milky Way at the center is saturated white because it's full. It's the brightest, the thing with the most heavy elements. Okay, but I love that because it shows, this stuff outside of the spiral galaxy that I'm also interested in. It tells us about how our galaxy formed and the things that merged with it. Okay, so these, I wanted to give you an example since that movie focused on the stellar halo. I wanted to show you the beautiful images that we are now making, that people are making from simulated galaxies. So none of these that you're looking at here is a real galaxy. These are all images of fake galaxies that we've created in supercomputers. And you can see we're entering an era where we're making these amazing looking galaxies compared to, they look like the real things. I have managed to fool observers with, asking them which one is real and which one is fake. Okay. Over on the right is one of my own simulations. So I wanted to include that. This is from a recent paper. I mean, we've used it in many publications throughout the years, but this particular simulation actually we made fully public. So if anybody out there is interested in actually playing with simulation data, this galaxy is available for you to actually play with. So you can just Google me and it's right on my website leading you to the data. Okay. All right. So here again, I wanted to show, right, this is our new simulated Milky Way. And here are all these little dwarf galaxies that I'm interested in. So my main motivation for running this galaxy at the highest resolution ever published was because as you get to higher and higher resolution, that means you also can resolve the fainter and fainter dwarf galaxies around it. Okay, and this is important, right? Because we are entering an era where we're discovering all of these new faint galaxies around the Milky Way. This is a fantastic image made by Josh Simon, showing all of the known neighboring dwarf galaxies of the Milky Way as a function of time, right? So originally, the very brightest ones you could see, and then a few years later, a decade later, we find some more faint ones. And as time goes on, these are basically the ones discovered through photography, right, with photographic plates. And then there's this big jump up in the early 2000s. And that is when we entered the era of digital sky surveys. So in particular, the Sloan Digital Sky Survey came online. And thanks to that, you can see that we actually found a whole bunch of new faint dwarfs that are orbiting the Milky Way that we didn't even know about before. And then about 5 years ago, the Dark Energy Survey came online and essentially doubled the number of known dwarf galaxies around the Milky Way. And in just 2 years, the Vera Rubin Observatory is going to come online, and it is supposed to discover hundreds, literally hundreds of these faint dwarf galaxies. So the reason I want to run simulations like this is to try to make predictions for what are these telescopes going to find when they make these discoveries. Okay. So this is just one example of the type of results that we're getting out. Okay, so this is a plot. I apologize, astronomers use magnitudes or these funny numbers. Brighter things are more negative. All right, but this is just a size, a plot basically of brightness versus size. And so all of the gray and black points on here are real galaxies that are observed nearby the Milky Way. And I actually ran 2 of these Milky Way simulations. So they're shown on here in blue and orange. And the gratifying thing is that they were the first simulations to ever reproduce this full range. You can see there's, at any given brightness, there's this range of sizes. And we were the first people to actually be able to explain the full range of sizes. And that means, you can only figure this stuff out if you run these really high simulations and you run these tiny dwarf galaxies in an environment like the Milky Way. That's the only way you get this type of result out. But speaking of the Vera Rubin Observatory, right? So this dashed line right here is supposed to be how faint the Vera Rubin Observatory can observe. So there's a question, right? People are asking, are there supposed to be dwarf galaxies in this range, in this little box? And in other words, are there going to be dwarf galaxies that Vera Rubin telescope won't find? And our simulations would actually say no. No, in fact, you should be able to find all of them, which is pretty exciting. So we'll find out, I guess. Well, maybe we'll find out if we got it right. Okay. So that's it. Basically, if you want to understand all of the diversity of dwarf galaxies that we observe in the universe, it looks like we've got to be able to simulate them in their preferred environments, that is around the Milky Way. And it allows us to make predictions for big telescopes that are about to come online. But doing this was really challenging. So one thing I didn't say is how much computing time this took. Right, so these simulations took about 100 million CPU hours. And so I try not to think at night about how I am personally melting the ice caps, because otherwise I just would never sleep. But, it is exciting to be able to get these new scientific results out. And these were the first simulations to ever resolve things this small and this faint. And it was thanks to this supercomputer, Frontera, which is sponsored by the NSF. So I just wanted to give them a shout out. So thank you very much. I'm done.
Thank you so much, Alyson. That's so really interesting to see. And that's such a kind of state-of-the-art simulation that you're showing us. And I'm actually quite surprised that you're saying there's nothing. I just assumed that the galaxies went all the way down like turtles, that there's no galaxies at that really faint level.
Well, to be fair, right, it's possible there's stuff below this plot, right? All right, so just to be fair, there is still stuff below our resolution limit, so maybe they'll find something down there, and then, I couldn't make a statement about it, so.
I see. And you said that your simulation took 1 million CPU hours. How long did it take for us in real life? Because assuming you're running on a whole bunch of computers at the same time.
Yeah, so this is a little hard for me to put together, because it was one of these things where it got started on the Blue Water supercomputer. It got transferred to the Pleiades supercomputer run by NASA, and then it got transferred to Frontera. And there were blocks of time in between all of those. So it was strung out over years. I can tell you that if it was done end to end, it would be at least a year running on, hundreds of nodes every day. So it was a lot of time. Yeah.
There's a really interesting question from the crowd, from Gordon. It says, do the large number of galaxies, the dwarf galaxies in particular, increase the estimate of ordinary matter? So like, as you find these things that we weren't seeing before, does that change this 5% for normal matter? Does it go up?
Right, that's a great question. Believe it or not, it actually goes in the other direction. So because when we find these faint things, we can actually use the motions of the stars in the galaxies to figure out how much mass is in them. And when we do that for dwarf galaxies, it turns out they have way, way, way more dark matter than they have ordinary matter. And so they're actually, we call them dark matter dominated. And so So then the question becomes, okay, there's supposed to be 5% of the matter is supposed to be in these galaxies. Where did they go? Why isn't it there? And so that's actually another open question that we're trying to figure out.
There was a little bit of a joke, I think, wondering if these big simulations, are they driving up the prices of GPUs? Are supercomputing?
They're not running on GPUs yet.
Okay.
they're not yet running on GPUs. That the code is going in that direction. It's being tested right now to run as a joint CPU GPU simulation code. But everything I just showed you was run only on CPUs, so I don't have anything to do with the GPUs at this point.
Cool, but that sounds like a really interesting direction for this kind of work. And then I saw like there was these really cool streams in the stars when you had these merging galaxies. Does that mean there's streams in the dark matter too, if you were to show that?
Should be, yeah, absolutely. Anytime you see those stars being pulled apart, the dark matter is also being pulled apart. Yeah.
And would that like have any kind of observational? Would there be any observational sign of that? Or?
People are trying to figure that out, right? For instance, right, we have these experiments on Earth where, it's literally, well, maybe we'll be hearing about something like this in the next talk. I'm not sure, but yeah, we have these detectors, right, that are hoping that a dark matter particle comes along and collides with an ordinary particle, and that we see that interaction. What if we're sitting in the middle of like one of these giant streams of dark matter that got ripped apart by a galaxy, right? Then we'd be sitting in some, an over density of dark matter, and that would throw off our results, right? So people are curious about that, and we have no way of directly looking for dark matter. So the only way to really do it is to try to figure out, using the streams of stars, should there be a stream of dark matter here? So people are getting better at looking for these streams of stars too. So we'll maybe be able to make some statement about streams of dark matter soon.
Cool. All right. Well, I think we're gonna end this round. But again, I encourage anybody tuning in. You can still ask questions for Alyson. There might be an opportunity to answer one or two after all the talks. But for now, we're gonna go to our next round of trivia. So thanks again, Alyson, everybody at home. I hope you appreciated that really cool talk. And, I've done something to my PowerPoint where now it doesn't want to do full screen view. I don't know what's happening. All right, it seems to be working now. Just have another beer. I think it makes the technological difficulties go down a bit easier. All right, so I hope you had fun with the first round of trivia. We're going to do 5 more questions before we hear from our last scientist today. So question number 6, and again, the form for the trivia is in the description of YouTube underneath the video. And so question number 6 is to name this object. What is this really cool contraption that we see in this image? And it is, I'm not referring to the pint, I'm referring to the image. Question number 7. We recently experienced a meteor shower whose source is an asteroid instead of a comet. It turns out that most meteor showers that we see from Earth come from comets. So the question is, can you name that meteor shower? What is the name of the meteor shower that came from this asteroid? And again, I will repeat all the questions. So we recently experienced a meteor shower whose source is an asteroid rather than a comet. Can you name that meteor shower? All right, question number 8. What is the word radar an abbreviation for? What does radar maybe stand for? What could it be? Question 9. Which is the strongest fundamental force in the universe? What is the name of the strongest force, fundamental force in the universe? It is not Superman. Just letting you know. Question 10. Are there planets in the solar system with no moons? And if you think there is, we want you to name it or them. Are there any planets in the solar system with no moons? All right, we will do it one more time fairly quickly. Name this object. What is the name of this object? Question 7. We recently experienced a meteor shower whose source is an asteroid rather than a comet. So it's a bit strange for a meteor shower. Can you name that meteor shower? What is the name? Question number 8. What is the word radar an abbreviation for? To be fair, I didn't know this one. I learned something new today. All right, question number 9. Which is the strongest fundamental force in the universe? We will also not accept unobtainium, even if it lets a craft drive or drill all the way to the center of the Earth in the crazy movie, The Core. Clearly I have The Core on the mind. Which is the strongest fundamental force in the universe? And last but not least, the last question of our trivia tonight is, are there planets in the solar system without any moons? And if you think there are, we want you to name all of them that don't have moons. All right, so that's the end of trivia, but that means it is time for our final scientist of the evening to be revealed to us. And so Miriam, I really would welcome you on to share your camera. So our final speaker tonight is Dr. Miriam Diamond. Miriam did her undergrad at Carleton, and then her master's in science and theoretical physics at the University of Waterloo. And that was through the Perimeter Scholars International program. And her PhD was done in experimental physics at the University of Toronto. Miriam did a postdoc at the SLAC National Accelerator Laboratory in California before returning to Toronto as a professor. She's worked on several astroparticle and high energy particle physics experiments, including the Sudbury Neutrino Observatory and ATLAS at the CERN Large Hadron Collider. Miriam is currently a principal investigator of the Super CDMS NOLAB experiment. And so her Super CDMS research has benefited greatly from the help of her coworkers and her very furry assistants, who are Quark, Quasar, and QWERTY, who are all guinea pigs. But I'm a little bit sad. I guess they will not be joining us this evening. They're already sleeping. But Miriam, it's so great to have you here. I'm looking forward to hear what you have to say about Come to the Dark Side. I'm going to stop sharing my screen, and I encourage you to share yours and unmute yourself. And I look forward to hearing from you.
Thank you so much. It's really wonderful to be here. I wish that I could see all of you in person. But it is still wonderful to have all of you joining us virtually. And my mission today is to get you all to join the dark side. And it's not just the dark side, it is the dark side beyond the standard model. Beyond the standard model of what? Well, beyond the standard model of particle physics. And this is a very ancient discipline. Going back literally thousands of years, humanity has been trying to figure out what are the fundamental constituents of our universe. What is the world around us made of? And even the ancient civilizations had their own ideas of what substances such as earth, air, fire, and water might be fundamental. Nowadays, we have the so-called standard model of particle physics, and it gives us all of the building blocks of matter and how they interact with each other. There are various different types of building blocks, sort of like there are different kinds of Lego in your set. Some of them are quarks, some of them are leptons, some of them are bosons, and the most recent piece of the Standard Model to be found was the Higgs boson, which garnered a Nobel Prize and made the news, and also appears in a lot of science fiction movies, which are better than the core. Okay, so we have this wonderful model, and it has stood up to several decades of experimental tests in particle physics laboratories. But it turns out that it is incomplete. And our first hint that the Standard Model was incomplete actually came not from particle physics experiments, but from astrophysics experiments. And so this led me and many other scientists into the field of astroparticle physics. So we have these two, what used to be very different branches of physics, now coming together to help us explain what's going on in our universe. So we have several different indications from astrophysics that there is some sort of stuff out there in the universe that is not described by the Standard Model. We can see the fingerprints, so to speak, of dark matter in the cosmic microwave background radiation, and in large-scale structure, and in what we call galactic rotation curves, which is basically charting the velocities of different stars in the galaxies, and seeing that, as the previous speaker said, the galaxy would fly apart if there wasn't something extra holding it together. So, so you've heard about all this. I'm now going to add one more piece of evidence, which is collisions between galaxy clusters. So this is a false color image. So the image is real, but the colors that have been added are fake. The blue represents the dark matter halo, and the pink and red represents stuff like gas and dust from when two galaxy clusters, one coming one way and one coming the other, collided with each other. And what happened was the dark matter in those galaxies simply went right through each other. And so they ended up at one end or the other end of the image, whereas the dust and gas and stuff that is made of Standard Model particles interacted with itself and sort of got stuck in the middle. And so what we see from these kinds of images is that dark matter seems not to interact very much, if at all, with ordinary matter. And this also explains why we haven't seen dark matter here in the lab, here on Earth yet. Dark matter can be everywhere in the universe, including right here in this room, but just interacting with us so feebly that it goes right through us and we don't notice it being there. So this leaves us with this question of, okay, if dark matter is some sort of subatomic particle that's not in the Standard Model and that interacts very weakly with the known Standard Model particles, what the heck is it? And you saw this pie chart before, that actually there's much more dark matter in the universe, we think, than there is luminous matter. So all of this Standard Model stuff goes in the luminous matter category, and we have to add to it something that makes up dark matter. The question is what? And this is what I have devoted much of my career to trying to figure out. Of course, it would be wonderful if it turned out that dark matter was made up of cute little guinea pigs, but it turns out that the answer is quite a bit more difficult than a guinea pig to observe. We do know that if you took a box approximately this big, there should be about one particle of dark matter in it. Yes, this is my mix. You have to mix dark matter in with luminous matter in order to make your own galaxy. Well, you're stuck in lockdown, you know, in your kitchen while you're baking stuff, might as well whip up your own galaxy Don't forget the dark matter, otherwise your galaxy will fall apart. There are actually many different candidates for what kind of new subatomic particle this dark matter might be. The first main idea that people had was that it was made out of so-called weakly interacting massive particles, or WIMPs. WIMPs for a few decades in various dark matter detectors here on Earth, and we have not found any direct evidence for WIMPs yet. So there are these other candidates that we now think dark matter may be, things like axions, which are actually not penguins, as cute as the penguins are. They're actually very, very low mass particles. It could be lighter WIMP-like particles. It could be self-interacting dark matter. So when I said that dark matter interacts very feebly with normal matter, well, that doesn't mean it can't interact with itself at some level. Or it could be something we've hypothesized called dark photons. Photons are the carriers of the electromagnetic force. In other words, they're quanta of light. And so we think maybe there might be an analogous force that we have never yet detected that exists between dark matter particles. And it would be dark light, or literally the dark side of the force, carried by dark photons. So we have several different search strategies for seizing control of the dark side of the force and taking over the galaxy. For scientific exploration of dark matter. One of these is supercolliders, where basically we smash standard model particles together at the highest energies that we can, and we look at what comes out, and we hope that maybe we will produce enough dark matter that if we have sensitive enough detectors, we'll actually be able to see evidence of some of it. Then there's what we call indirect detection, where we basically hope that particles of dark matter floating around in space will interact with each other somehow and produce standard model particles that we can see in, for example, very sensitive telescopes or space probes. And then there's what I mostly work on now, which is direct detection, where we set up on Earth a detector made, of course, of standard model particles, and we wait for a dark matter particle to come along, bonk into the detector, and then the dark matter particle probably goes off on its way again, but it has some tiny effect on the standard model particle. It bumps into it and maybe deflects it, for example. And then maybe we can detect that tiny bump in our detector, literally things that go bump in the night. So a little more about each of these search strategies. Currently, the most powerful super collider in the world is the Large Hadron Collider at CERN, which is what made big news for discovering the Higgs boson. And in fact, now that we have found the Higgs, the search for dark matter is one of the next major priorities of the collider. And the idea with this type of experiment is when we smash bunches of protons together at very near the speed of light, we have all kinds of standard model stuff coming out. And maybe, if we're lucky, we'll also produce some dark matter particles. And if we do a really good job of reconstructing all of the standard model stuff that comes out, maybe we can see sort of the fingerprints of this missing dark matter stuff. It's kind of like looking for a needle in a haystack, though, a very, very large haystack where the needles are actually invisible and you have to feel around for them. There's also a variation on super collider searches where instead of colliding two beams of particles, you collide one beam of particles with literally a fixed target. And so this could be, for example, a very dense plate of metal. And when the beam hits the target, you have all sorts of standard model particles produced. But you can put what we call literally a beam dump. So this can be, for example, a large amount of concrete behind the plate, where almost all of the standard model particles should be absorbed. So you can imagine how thrilled my parents were when I told them, what did I do today? Well, I was digging around in a dump and messing around in the dirt in order to set up an experiment. Why? Well, because if we put a detector behind the beam dump and behind, say, a bunch of dirt, and we actually detect some particles there, that indicates to us that maybe the particles went all the way through all of this stuff, which most standard model particles wouldn't do, and maybe it's dark matter that was produced from the particle beam. So then there's what I called indirect detection, which is when dark matter particles collide with other dark matter particles in space, we have theories that tell us what kind of standard model particles might come out of that. And then if we set up a very sensitive space probe, for example, we will see standard model particles such as positrons, electrons, neutrinos, protons, antiprotons. And if we analyze very carefully exactly what energies these particles were and where they were coming from, perhaps we can see a signature of standard model particles emanating from dark matter collisions. So after all that, I'm now going to talk about the type of experiment that is nearest and dearest to my heart right now, which is direct detection. So we are sort of on an arm of this beautiful spiral Milky Way galaxy, as you heard earlier, and we are actually rotating around the center of the galaxy at something like 270 kilometers per second. Stop and think about that for a second, how fast you're moving just because of the motion of the galaxy. Okay. And so if our hypotheses are correct, we're actually moving through this dark matter halo. And it's equally correct to say that the dark matter halo is moving relative to us, as it is to say that we are moving relative to the dark matter halo. So what it would look like to us is sort of this wind of dark matter particles coming and hitting us. And so we can set up an Earth-based observatory and hope that this dark matter wind will produce interactions that we can see in our detector. So far, the status of these searches, well, there's two ways of looking at it, depending on if you're a romantic at heart or a cynic. My love for you is like dark matter. You can't see it, but it is always there. Or my love for you is like dark matter, still haven't found it. Well, we still haven't found it in the lab. And in case you're wondering, with Valentine's Day coming up, yes, I am still single. But my next attempt at finding love, at finding dark matter, is called Super CDMS. CDMS being short for Cryogenic Dark Matter Search. And it is hosted at SNOLAB, which is Canada's premier astroparticle physics facility, which was made famous a few years ago when Art McDonald, the former SNOLAB director, won the Nobel Prize, or was a co-laureate of the Nobel Prize for the discovery at the original Sudbury Neutrino Observatory experiment that neutrinos have mass and oscillate between three different types. So this facility has an illustrious history of making groundbreaking scientific discoveries, and I'm hoping that the next one will be dark matter detection. What's interesting about this facility is it is 2 kilometers below the surface in a mine shaft. Now, why would we stick a dark matter experiment all the way at the bottom of a mine shaft? Well, clearly it's because we need a very secret facility in which to set up our lair. And of course, since we are the Dark Lords, we would put it deep down in the bottom. No, it has nothing to do with that. Actually, we put our apparatus underground to shield it from cosmic rays that are constantly raining down on us at the surface and that would mess up our very sensitive detectors. So all the way at the bottom of the mine shaft, you go down a deep, dark hallway and you find our Super CDMS experiment, where we put very sensitive particle detectors at the center of basically a whole bunch of shielding. So what is in those detectors? Well, the reason that cryogenic is in the name is that everything is done at super cold temperatures, very close to absolute zero. And in those super cold little areas in the detector are sitting these beautiful semiconductor crystals. So these are very pure crystals made of silicon and of germanium. And what we hope is that when a dark matter particle comes in, it will either hit a nucleus or it will hit an electron in our crystals, and it will cause either a recoil of the nucleus or a recoil of the electron. In other words, the nucleus will get bumped and kind of shake, or the electron will get bumped and will get dislodged from its orbit. And so these are the signals or the fingerprints of dark matter that we're looking for. And what's very exciting is we are expecting our first operations next year. So stay tuned, everyone. And I hope I have convinced you all to come to the dark side.
Thank you so much, Miriam. And I have to say, if you were to put a very secret layer 2 kilometers underground, convincing us it's not a layer is exactly what I would expect.
Oh, yes, of course. That is part of my job. I'm glad I've been convincing.
So there were some really cool questions. One maybe is from a relative of yours named David Diamond, or maybe it's a coincidence.
Uh-oh, that's my uncle. Hi.
All the aunts and
uncle
uncles.
in Montreal. Hey.
Very good. So he raised a point, which I'm turning into a question, is that could it be possible that dark matter just doesn't interact with normal matter? Like, why do we think that maybe it does?
Yes. So the only thing that we know for sure in terms of dark matter interactions is that it interacts gravitationally. So that's sort of an indirect interaction with normal matter, in that normal matter also responds to gravity. So dark matter and normal matter kind of tend to clump together. We do actually have other reasons, though, that we think there should be some sort of what we call a portal between the standard model and what we call the dark sector. So that, for example, just after the Big Bang, these two sectors would have been in thermal equilibrium with each other. And then the dark matter would have gradually frozen out as the universe expands and cools. There's also variations where you have sort of a freeze-in model instead of a freeze-out model. And there's various sort of different cosmological histories that we can tell, partially because, as one of the previous speakers said, we cannot directly see back in time before the cosmic microwave background. So we don't know what was going on in the really early universe. But we have reason to believe that at some point, the dark sector was in thermal equilibrium with the standard model, which requires some sort of interaction between them. Part of it, I have to admit, is also just optimism, because dark matter is a heck of a lot easier to detect in the lab if it does have some sort of non-gravitational interaction with the standard model. If it turns out not to, and that the universe is just set up in a really strange way just to screw with us, it's really going to be frustrating.
I can understand that. Another good question was, does dark matter orbit in the galaxy like normal matter?
Well, actually, the person who can probably best answer that question is the person who does the simulations, which is the previous speaker. So I mean, part of the detailed behavior of dark matter versus normal matter depends on exactly what properties you endow the dark matter particles with. But maybe we can go back to the previous speaker and she can talk a little about how it looks in her simulations.
Alyson, you can come back now, or we could just save this question for the panel. So I think you're already here, so you should.
The short answer is yes. So yes, it does orbit, just like the other stuff.
Cool. Interesting. And maybe we'll have a follow-up question with that in a little bit. But thank you for sharing, Alyson. Another question was if there's, where does it go? Right. Is there any sign through the indirect portal, the indirect detection of turning into standard models? Is there any signs yet that like from that, are we seeing anything there?
Oh, there have been some really tantalizing clues, actually. And so lately we have seen some stuff, for example, that seems to be coming from the very center of our galaxy. And we have sort of struggled to figure out whether we can reconcile it entirely with the standard astrophysics models, or if there is some dark matter signal coming from there. One of the problems that we have is that one of the signals we're seeing could either be dark matter or it could be what we call millisecond pulsars. So pulsars, these are basically stars that were very big, but then collapsed on themselves once they ran out of fuel. And so they collapsed down to what we call a neutron star, where the matter is so dense that it's literally in the form of just neutrons sitting closely packed near each other. And these neutron stars are actually spinning around and spitting stuff out from their poles. And they're spinning so fast that they literally spin like once or more every single millisecond and spit this stuff out as they turn. And it turns out that the stuff that they spit out, if there's a lot of them near each other, can sort of look like a dark matter signal. So for about a decade now, we've been very closely watching these signals coming from the center of our galaxy, and we're not yet quite sure what they are.
Cool. Well, thank you. So what I'm going to do is do the reveal for trivia. So for the trivia questions, get your last answers in. Once I start reading answers, you're no longer eligible for being considered. So make sure that you submit that form now. And then I will invite all three speakers to come back. And I think there's a few follow-up questions that I saw. And I encourage anybody that has a question for any of them, or maybe they have questions for each other, we can have a bit of a discussion before we call it at the end of the event at about 8:30. So let's see if I can actually share the screen this time for, yes, it's working. Technology. We can do so much with technology. So it's time for the reveal. If I can click. So trivia round one. So I'm going to start with the round one questions. And that was, how much would a 150-pound Hilary Swank weigh when she goes to the center of the Earth in the core? And if she got to the very center, she would weigh 0 pounds, but she'd have a lot of weight on her shoulders. So her weight would be 0. Question number 2, what constant is referred to as the universe's clock? And this smart fella, I think, was mentioned maybe in the comments, who gave the answer is the speed of light. And of course, Einstein was one of the main people that stipulated that that was a constant. Question number 3, which one of these planets radiates more heat than it gets from the sun? Jupiter, Saturn, Neptune, or all of the above? And the answer is all of the above. So actually generating more heat on the inside and then radiating that away than they're receiving from the sun. Question number 4 is a name that was mentioned tonight by Alyson. That is Name the Scientist. This is a picture of Vera Rubin, who the Vera Rubin telescope is named after. It is not a coincidence. Question 5. David Bowie played which famous inventor in a Christopher Nolan film? It's a very, very good movie. I really recommend it. David Bowie played Nikola Tesla. And that's it for round 1. I'm just doing time so I know when the cutoff was on the trivia. Trivia round 2. Question number 1 was, name this object, and that is the International Space Station. Question 7 was, we recently experienced a meteor shower whose source was an asteroid rather than a comet, like most other meteor showers. What was the name of that meteor shower? It was the Geminids. So you might have caught that in around December 10th or so, if you're willing to bear with the cold, but it's usually quite a show. Of course, it wasn't a show here in Kingston. I think we clouded out that entire week. I was very upset. I wanted to see them. All right, question number 8. What is the word radar an abbreviation for? And it turns out radar stands for radio detection and ranging. Question 9, what is the strongest fundamental force in the universe? It is not Superman. We are not accepting LERV. Instead, we are accepting the strong force, or the strong nuclear force. Just as a note, you might think something like gravity, it's holding galaxies together, it's holding, forming black holes. Turns out the strong force is 6,000 trillion, that's 39 zeros after the 6, times stronger than the force of gravity. If you can get close enough to feel it, I guess. So the answer was strong force. And question number 10 is, are there planets in the solar system with no moons? And if so, we asked you to name them. And as you can probably guess, based on the wording of the question, the answer is yes, and they are Mercury and Venus. So that's the answers to our trivia. I hope it was a little bit fun, and I hope you submitted it. We'll go through those after the event, find those winning or the highest score, and also pick a random one, and reach out to you by email to find out how we can send those to you in the mail. All right, so that concludes the trivia. We just have a couple minutes left. I'm happy to go maybe a couple minutes late, but I would like to welcome back on all of the speakers from tonight. And we did have a few extra questions that maybe there's an opportunity to ask those questions, and maybe you guys have some questions for each other, because I feel like that's one of the things. If we are all a little in our silos, we don't have a chance to talk to each other. So this is an opportunity to do that. I want to thank all of you for fantastic talks. It was really interesting to hear from each of you. And sorry to Simran and Miriam if I happen to talk up Alyson's talk a little bit more than your guys's. It is the kind of research that I also do. But one of the questions is, and maybe I don't know, is there any more to talk about on that question about how dark matter orbits in galaxies? Does it orbit like the exact same way, or does it have different orbital characteristics? And does that come out, and maybe how you could detect it with a detector?
It's really not doing much different. It doesn't have, say, any extra velocity compared to the gas and stars, right? It actually falls in with the gas. It doesn't have any extra kick to it. And so it orbits pretty much just like stars would. The thing that's actually special is gas, right? Because gas can cool, right? It can emit photons, and so it can get colder and denser. Dark matter can't do that. Stars don't do that, right? And so the thing with gas is it can cool and collapse and form that nice disk galaxy, spiral galaxy that you see. But dark matter is actually going to stay puffy, right? It's going to be in a big round sphere, but moving through the galaxy at about 270 kilometers per second, something like that.
I see. Cool. There was a question for you, Simran, which was, like if there was no technological, well, maybe not technological, but there's no like financial limit, which is like, what kind of detector would be great to build for detecting these kind of gravitational waves?
That's a great question. If only I was an instrumentational person. I know that there has been some like lab scale gravitational wave detectors that have tried to detect these gravitational waves. For anybody who knows what it means, like at the megahertz, gigahertz ranges. They're only able to run for a short amount of time though, so they don't have like a really great bound. Like, the plot I showed, the bound that they put is so much higher than what we already have, but it is like a proof of concept, so it can be done. But for the more, near term, it's more like better CMB and galaxy experiments to lower it. Because the other one also depends on the fact that gravity isn't just acting just like a normal force. It would have like another one of these, beyond standard model particles. If it was a gravitino, which is like a beyond standard model thing, it can interact with these types of lab scale gravitational wave detectors. So, there's quite a bit of ways to go there. And I'm not necessarily the person that knows about that as I do simulation work.
Fair enough. Well, that was still really cool. I was wondering, do you guys have any conversations or questions for each other that you maybe didn't have the opportunity to ask?
Oh yes, I have a very important question for Simran, which is, can you provide me with the recipe for this potato salad that you're talking about that 1,000 people bring to the party? I mean, I'm not having any parties, obviously, now in lockdown, but I'm thinking I could make myself a nice potato salad, have a party for me and my guinea pigs.
Yeah, I'll be sure to send over a guinea pig friendly potato salad recipe.
There is a question for you, Alyson, although I have to say that based on Simran's affinity for baking and cooking, I'm sure I can count on whatever that potato salad recipe is to be quite tasty. But Nick, who's behind the scenes, has asked Alyson, what is the resolution? Like, how sensitive, what are the smallest scales in your simulations?
All right. Yeah, so the reason I call it the highest resolution ever of a Milky Way is because, so let me back up and say the big picture is, we start all of these simulations soon after the Big Bang, we run to the present day. Initially, it's just gas and dark matter, right? The stars have to form later in the galaxies out of the gas. And when those star particles form, they are not individual stars, right? Historically, they have been, say, 1 million solar masses, right? That's, literally 1 million times more massive than the sun. So they actually represent clusters of stars that are forming together. And what is the reason I say these are the highest resolution is because now we are forming star particles at just under 1,000 solar masses. And I've run individual dwarf galaxies away from Milky Way where we're getting to hundreds of solar masses. And so now we're getting much closer, right, to the scale of actually forming individual star particles. But they are still, technically they are still clusters. They're just like clusters of 1,000 solar mass now. So, yeah.
And does that resolution limit, because you were saying on that plot, like maybe there's more stuff down there. Does that resolution then play an important part in what you can say there is or isn't?
That's exactly right. Yeah, if I could get all the way down to, tens of solar masses or even 100 solar masses on that plot, then yeah, I'd be able to go further down in brightness.
Cool. There's another question for you, Alyson, actually, which was, why was the dark energy survey, like it sounds like it's something that's looking for dark energy. Why was it really good at finding these dwarf galaxies?
Yeah, and it is looking for dark energy, but it happens to be staring at a patch of the sky really deeply. And so you get, another man's trash is, our treasure, right? So you stare at a patch of the sky for a long time, you add up those photons, you find faint things. So that's how it works.
Cool. I think we're going to wrap up unless there's any last burning questions out there in the universe or among our panels or people that are behind the scenes running things. Let's give you a last moment, but if I don't see any, I think everybody's just saying thanks. Some people are saying maybe add a dash of dark matter to your potato salad. So I think everybody's just now hungry and is looking forward to maybe to close out the night with some food. So I want to really thank each and every one of you again for a fantastic sequence of talks and just getting to hear from each of you and then engaging with everybody at home. Thanks for joining in. And we don't know when our next Astronomy on Tap is going to be. We have the Mars event next month. The McDonald Institute will be running an Ignite event in March, on March 4th. So stay tuned for information about that. But otherwise, I hope everybody stays safe and take care. Thank you.